Welcome back to my series on sequential decision analytics. This module is going to just be on state variables. So state variables are an incredibly important topic and one that's very poorly understood. So I'm going to start off talking about defining state variables, describe a network routing problem, touch on belief state variables, then the very important topic of pre- and post-decision state variables, and then finally I'm going to illustrate a sample of state variables and how to create state variables from an actual problem from the modeling process. So I love this conversation. This is a depiction of me speaking to my former colleague Erhan Schindler. Erhan was also earlier in his career, he was the leading probabilist in stochastic processes. In the 1970s, he wrote the most widely used and referenced book, a graduate level book on probability and stochastic processes. And when I started to realize this issue with state variables, I went to him and I said, Erhan, what's the definition of a state variable? And he literally looked up at me and said, that which cannot be defined. And that's an exact quote. And so here we are. This is what illustrates how mathematicians can use the word state in text. They can use it in equations. They can prove all kinds of theorems. They have mathematical properties, but they can't actually define it or even use it to model a real problem. I love to use this illustration on the left-hand side. This is when probabilists talk about illustrating a state variable, they use things like a tic-tac-toe board, or from the Princeton reinforcement learning course. This is a diagram where there's a problem with a small number of states that you can be in, A, B, C, D, E, and then you have transitions between the three states. I like to use this image of a buffet. To me, this is what a state variable looks like. It's multidimensional and rich, and the information comes in different flavors and qualities and whatnot. That's what real state variables look like. So what is a state variable? So the MDP community, Bellman's classic text on dynamic programming in 1957 describes the state variable with, we have a physical system characterized at any stage by a small set of parameters, the state variables. And he italicized state variables. So this was his definition. Fast forward to Putterman, 1994, the most popular book on Markov decision processes, defines a state variable on page 18 with, at each decision epoch, the system occupies a state. And again, he italicized state to emphasize that this is where he was introducing it. When I asked my colleagues at Princeton about this, one just dismissed me and says, just go to Wikipedia. Well, here's Wikipedia. A state variable is one of a set of variables that are used to describe the mathematical state of a dynamical system. So when I was in grade school, I learned that when you define something, you can't use the word in the definition, and yet that's exactly what all three of these definitions do. So I have a more thorough discussion of this, but to highlight, so the good news is there are some books that have what I consider to be a perfectly good definition of a state variable. Kirk, 2004, and the book by Cassandras and La Fortune in 2008. These are both classic optimal control books, deterministic control. And I'm paraphrasing, but both of their definitions are equivalent to a state variable is all the information you need at time t to model the system from time t onward. Absolutely fine. That is what a state variable is. The only thing that's missing is they don't say what information. So that's what I'm going to now add to this. But let's just be very very clear. These two books, now it turns out that not every book on control from the controls community has a definition, but these two do. And I think that I can say, well, this is well known in the controls community. Now, I will emphasize these are people from deterministic controls. Deterministic controls are typically engineers at heart. And so they're much better at modeling. And I have generally found the community of deterministic control to be the best of all the communities. It's not that they don't use uncertainty. They don't have a lot of sophistication in it, but boy, do they have they're best grounded in terms of their modeling. My definition of a state variable in my big book, I have two flavors of state variable. One is the policy-dependent version, because generally we are specifying the policy, but there are three functions. So the policy-dependent version is a function of history that is necessary and sufficient to compute First, the cost of contribution function, and you see the letter S there. There's the contribution function, and I have to have the information needed to compute that. The decision function, which is the policy, which depends on the state. You have to look at how you're making the decision. And in this policy dependent, I'm assuming that somebody has come with a policy, and not always true, but often true. And then the third one is that we have the transition function. Now, the transition function, sometimes there are problems where I have information I need for the future. I don't need it at time t. I don't need it for the cost or the policy at time t, but I will need it in the future. I'll illustrate one of these shortly. And then you also have the exogenous information process. So we have these three functions. Now, I will say there's actually sort of a fourth function. That W process is actually sort of a fourth function. I can call that an embedded function. So there's these three types of functions, but technically it really should be potentially four. The optimization version does not have a given policy. So I replaced the decision function, which is the policy, with constraints. So the constraints are a function of the state variable. It's usually the case. And so now I have three functions, but now it's the cost function, the constraints, and then the transition function. But this is the information, which means once you're done your modeling, you look at your cost function, you look at the policy, you look at the transition function. At the end of this module, I'm going to give you an actual example illustrating this process. Now, from Putterman, he's got this section. This is screenshotted from the book, the Markovian versus history-dependent dichotomy. So probabilists with Putterman's background, they love to talk about Markov processes versus history-dependent processes. The Markov versus history-dependent dichotomy, as he puts it, describes the information used by the decision maker when choosing an action. A Markovian decision rule uses only the information state at the current decision epoch to select actions, while a history-dependent decision rule considers some or all of the previous states and actions and up to including the current state when choosing an action. I claim this demonstrates a fundamental misunderstanding of what a state variable is. Okay, and I'm sorry, but this whole statement makes absolutely no sense when you use the definition that both I use and the one by the two control books. A state variable, by definition, includes whatever information you need from history. So there is no difference between state-dependent and history-dependent. In fact, you don't even need the word Markov because all properly modeled problems are Markovian by construction. So you don't even need this adjective. Now, there's a class of problems where you have hidden information that I can't observe. For example, I may have I did a problem in energy where it involved big transformers. These are the massive pieces of machinery that turn power from the grid at 100,000 volts down to 20,000 volts and eventually down to the 220 volts that come into your house, okay? These transformers last for decades and then they eventually degrade and blow up. And knowing the state of those transformers is hard because it has to do with things buried way inside. In fact, any complex machinery has states of little parts inside the machine that I can't observe. So these are called hidden state variables. Now, the way we handle those properly is to put a belief on them. And so you don't know it, so you have a belief. Okay, fine, you have a belief. That's your state. That's your state of knowledge about a system where you don't know everything. And that's perfectly fine inside the state variable. Okay, so here's a little example of where information not needed at time t is in the state variable. Let's say I have a time series price model. And I've decided to model my price process that the price at time t plus 1 is theta 0 times pt plus theta 1 pt minus 1 plus theta 2 pt minus 2 plus a noise term. So I can roll that vector of the three p's up into a vector p bar. That p bar is pt minus 1, pt minus 2. I claim p bar t is the state of the price process. It does not include pt minus 3 because I don't need that information. It does include pt minus 1 and t minus 2 because I do need it. Now, Putterman would say that this is non-Markovian. He thinks the state is PT. And that's just indefensible because what he's doing is making a distinction between information that just arrived versus information that arrived one time period ago or two time periods ago. Nobody cares when the information arrived. They just care what I know. So this whole notion of information from previous states like pt minus 1, I'm sorry, it's all information in the state variable. So p bar t is the price state variable. And the reason why I need t minus 1 and t minus 2 is because I need them in the future. So I don't need them to make a decision at time t. I need them to model the price pt plus 1, and then pt plus 2, and then pt plus 3, and so on and so forth. I don't need pt minus 3. So there's our state variable. Now, state variables, let's divide it between S0. The initial state includes parameters and functions that are fixed over time, initial functions that may change over time, initial values of quantities, like inventories, initial values of dynamically varying parameters, and initial beliefs about uncertain quantities or parameters. The dynamic state variables for t greater than 0 is any quantities, parameters, or beliefs that may change over time. And by the way, this is rare, but sometimes a function can change over time. Maybe I may change how I'm forecasting or how I'm making decisions. So if your function can change over time, then that's also in the dynamic state variable. Okay, network routing problem. I normally do this with a live audience, and I start off by asking for 4 volunteers. So get ready, because everybody watching this talk, you're going to have to be the 4 volunteers. All right, we have a basic graph I need to get from node 1 to node 11. So I start off at node 1 and go to node 3, and then I go from node 3 and go to node 6. What is my state? What's the state of my traveler? What's the state of my system? Now, all the travel times are constant and known. The graph is known. Okay, I'll give everybody a few seconds. And ta-da! Yes, the state is node 6. Nothing complicated. Every shortest path algorithm uses this as the state variable. All the travel times and the structure of the graph are in S0 because they're not changing over time. I have a static graph. Okay, let's assume I have a dynamic graph, and all these travel times are random variables. However, when I arrive at a node, I get to see the travel times out of that node. Okay, so let's say I go on to node 3. Once I arrive there, I get to see all the new travel times out of node 3, but the other travel times vanish because if I ever revisit node 1, it starts all over again. And then from node 3, I'm going to go to node 6. Once again, the other times go away, and I get revealed 3 new travel times. What is my state? Take a few seconds. It's all the information I need to make a decision. I need to know the node that I'm at, node 6, and I need to know those 3 travel times because I need that information. It's been revealed to me. Now, by the way, all of those probability distributions, I'm assuming, are static. So they're in S0. Okay, I put the node 6 in my R variable, and I put all of those other travel times in my I variable. They're other parameters. Okay, third problem. I'm going to do a little twist. Left-hand turns. If you make a left-hand turn from node 6 to node 5, I'm going to add in a penalty of 0.7. Okay, this is the trickiest one. I'll give you a hint. This is the trickiest one. What is my state? If I'm making a left-hand turn from 6 to 5, I would add in the penalty of 0.7. Well, the problem is I have to know, am I making a left turn? And in order to know if I'm making a left turn, I have to know what node I'm coming from. So right now, in the past, I've said I'm at node 6. I didn't say where I was coming from. I mean, I showed it on the picture, but I didn't store it in my state variable. Maybe I got to node 6 from node 7. So what I'm going to have to do is I'm going to have to say, well, my current physical state is node 6, still is. My information variables is, first of all, that vector of travel times and the previous node, node 3. That goes in my I variable. And so I have to now know that I'm coming from node 3. So yes, 6 to 5 would be a left-hand turn, and I have to add in the penalty. Okay, Now my favorite problem, this is a modified version, but it's right out of Putterman's book. We want to find the best path from node 114 that minimizes the second highest arc cost along the path. Okay. And oh my gosh, when I saw this in Putterman's book, I nearly died. Let's assume that I'm already at node 9. What is the state of my traveler? Okay. So we want to minimize the second highest arc cost along the path. So in order to know the cost of the path as I step away from node 9, I have to be able to say whether or not that next link changes the value of the second highest arc cost. So everybody look at this. Take a minute to think. Clearly, we still need node 9, but I also need to know the highest and the second highest costs on the path up to node 9. So if I look back, the highest is 15, the second highest is 12, third highest is 8. I don't need to know that, okay? Because as I step away from that, let's say I go from 9 to 13, well, the cost of that is also 13, which is higher than 12. 13 would become the new second highest, okay? Now, I include this partly because Putterman gives this example, but he still insists the state is a node 9. And then he goes through a discussion how Bellman's equation no longer works, and that, yes, under certain conditions, Bellman's equation no longer works. No, Bellman's equation always works. Now, I haven't covered Bellman's equation yet, but we'll be getting to it. But this was a fundamental error because he failed to realize what the true state variable was. And so this is something where a misunderstanding of the state variable it's not well known. It's not even not well known by leaders in the community. And so this is something that if you can come in and move forward with the idea that state variable is all the information you need to model the system from time t onward, the definition given by those two control books, you're a step ahead of an awful lot of people. And you would be able to come in and go, oh, I need the 15 and 12. There's a lot of complex stochastic dynamic systems where understanding what information you need is very important. And what I'm going to be doing is telling you how to figure out that information. It's what's in the performance metrics, it's what's in the policy, and I might need it in the transition function because I need it in the future. Okay, I slipped in one more problem. This is a stochastic graph with generalized learning. So as I progress out from node 1, as I make those observations, what I'm going to do is update distributions. Now look here, I got to node 3. Now, so let's say this is a Manhattan type of grid, and I observe these costs 8.1 and 3.6. Now, maybe I've observed something that's really high congestion, or maybe it's lower congestion, but simply getting those observations allows me to update the distributions in the future. Again, if I see that things are really highly congested, maybe there's congestion all around the network, there will be downstream congestion. And so now those probability distributions are not static, they are dynamic. So my state variable is going to consist of I'm at node 3, I have my other information, and I have my belief state, which is all of these distributions because they are dynamically changing. Belief state variables. Okay, very briefly. Belief states, we can have lookup tables. That is, for every x, I have a mean and a precision or variance. I can have correlated beliefs where I have a vector of means and a variance covariance matrix. I can have sampled beliefs. So those first two is what I would use in Bayesian belief models. The third one could be a vector of probabilities where I say, hey, I have a set of curves. I have 3 different types of theta that give me completely different curves. I don't know which set of thetas is the correct one. I have a probability for each one. That's my belief state. So belief states, now I can do updating. We can do recursive updating with lookup tables. I can do recursive updating with linear models. As we learn, I can't do recursive updating with nonlinear. When you're doing recursive learning, you can look at the recursive equations and pick out the belief state. So look on the right-hand side and look at the information you know, in this case at time n minus 1, that you need to model the system at time n, and it's mu bar and this sigma hat. If you come over to the linear models, I need to know the prior estimate of the vector theta. And this matrix M, if I have 3 variables in theta, the matrix M will be a 3 by 3 matrix. M is basically hiding the covariance matrix. I just never have to invert it. But if you tell me theta n minus 1 and the matrix M, I have all the information I need to move forward. Everything else here is information that arrives in the future. So my state at time n is the vector and the matrix. By the way, take a look at your state variable. This state variable is often very high dimensional and continuous. So the notion of discrete states just goes out the door. Okay, very important concept, especially when we're using Bellman's equation, is the concept of predecision and post-decision states. Predecision, the state variable is predecision. It's the state before you make a decision. So when you say state variable, you mean predecision. I don't think everybody needs to go running around calling predecision. You just have to know that the state is the state just before you make the decision. That's how we come up with state, because the reason we have the state is to make the decision. Now, there's something called the post-decision state. This is the state immediately after you make the decision. This was a term first introduced by Ben and Roy, who shared it with me. He put it in some minor paper. For me, it was life-changing because I was working on a problem where this was the great insight, because the post-decision state is a deterministic function of the pre-decision state. Now, the concept of post-decision state, Ben gave it the name post-decision. I think that's the right name. Sutton and Bartow used the term after state. It is the same thing as the outcome node in the decision tree. If you, at the bottom line, if you take our state decision information, and insert the post-decision state, notice how I use the state variable st. I put a superscript x because it's the state after the decision x. That way I don't use a whole new variable for state. Notice that it's still indexed by t because once you make a decision, no time has passed. That is, no new information has arrived, so that post-decision state is a deterministic function of the pre-decision state and the decision. Let me illustrate this in the decision tree. Here we have our pre-decision state where I make the decision. Here I make one of two choices. That's the decision. It takes me to these, what the decision tree people call an outcome node. That's the post-decision state. Then you have the exogenous information that takes you to the next pre-decision state. Here's a little inventory problem. Our basic inventory problem is you take the old inventory R plus X, let's assume it arrives right away, subtract off the demand, and that allows me to compute my next inventory. So I can break this down into 2 steps. You can go from pre to post. So you take RT plus X. That's RTX is the post-decision state. That's the inventory after my new product arrived, assuming it arrives immediately. And then going from post-decision to pre, I take the decision after my new inventory has been added, subtract off the demand, make sure it doesn't go negative. That then gives me my next pre-decision. In the post to pre step, there's no decision making. There is a random outcome d hat. So the first one has a decision problem. I have to determine x. And the second one has a Monte Carlo sampling or a stochastic problem. Now, here's my time-dependent version of Bellman. Vt plus 1 is the max over x's, your cost or reward function there, plus the expectation of the value function. Now, the Bellman people have no problem putting in that expectation. When you're optimizing, when you're having to solve that max problem, that expectation is really annoying because usually you can't compute it. So now you're having to do some high-dimensional integral or Monte Carlo sampling. If you go from pre to post, when you go from pre to post, the post-decision value function, notice how I put a little x in the v. The post-decision value function is a function of the post-decision state. This is a deterministic function of x. That means the max over x is now solving a deterministic optimization problem. This is a very big deal if x is a vector. I mean, it's huge. It's life-changing. But even if x is a scalar, it's still a lot simpler because I can do my x without having to deal with the uncertainty. Now, going from post to pre, I just have to do or approximate an expectation. I'm usually using a Monte Carlo simulation to do that, but no decision making in there. Okay, sample of state variables. State variables can come in all kinds of forms. They can be scalar, and they can be vectors, and they can be high-dimensional vectors. They can have mixtures of discrete and continuous variables. It can be that buffet. People have to realize a state variable is information, and it's all the information you need to make a decision. And as you get to more complex problems, the information you need to make a decision become very complicated. So I'm going to take a little energy problem and show you how to construct a state variable. And what I'm going to do is step through this little example of an energy problem. And anytime I see information that I need, I'm going to put a red box around it. That's going to be a hint that that is information that I'm going to need in my state variable. So let's start off with decision variables. So I have each of the blue links is a certain amount of flow. Those are decision variables. I have constraints. The constraints are subject to the energy from the wind farm, the load from the building, and the R is the amount of energy in the battery. The grid is assumed to have infinite energy. And so the ET, LT, and RT, that's information I need at time t. I'm going to need that information. So I'm going to put a red box around that. Now let's do the transition function. Now the transition function, I have all the equations for updating it. Notice that I have my price equation that needs, to get PT plus 1, I not only need PT, I need PT minus 1 and PT minus 2. The E, which is the energy in storage, it is a basic inventory equation. The demand at time t plus 1, that's going to be what I forecast it to be plus random noise, where that forecast is assumed to be provided exogenously. And then the R for the battery, the E was the energy from the wind farm that just evolves stochastically, and the R from the battery is basically an inventory problem. X, by the way, can be positive or negative. The objective function. So the only piece of information I need in the objective function is the price, and that's the grid price. So now I have information of the price of electricity, the constraints. In the look-ahead policy, I may need the forecast, and the transition function, I'm going to need those prices. Pull them all together, and that's my state variable. Recall that F is a vector of forecast, so that's a full vector. So this is a decently high-dimensional, and this is still a toy problem. Okay, so when you read about these simple, oh, here's a state variable, and here's tic-tac-toe, or here's a simple graph, this is an actual real-world state variable. Time series modeling. As I said before, when I'm doing time series modeling, I need my P bar vector. That's the PT, PT minus 1, PT minus 2. I'm going to need my current vector of thetas, and that matrix, if I have three-dimensional theta, I have a 3 by 3 matrix M. That all pulls together and becomes my state variable. Okay, so more on state variables. Go to our website, click on modeling. There's a whole entry on state variables. I really emphasize state variables because this is so important. And it doesn't matter what method you're using, because the state variable is the information you need to make a decision, no matter how you're going to make the decision.